Hi, Statistics. I got some requests for problems to be worked out for some problems in the end of the 6.2 homework. So problems 8 through 12, I've had a couple different people ask about. So I thought I'd go ahead and make this video showing you guys how to work out these particular problems. Realize that the numbers that I have on my screen may look different from the ones in your homework, but it will give you a sense of how to work these style of problems. So problem 8 is talking about percentiles. So it says assume that adults have IQ scores that are normally distributed with a mean of 100.4 and a standard deviation of 16.6. Find the first quartile Q1, which is the IQ score separating the bottom 75% with the top 75%. So for these particular problems, I went ahead and worked them out ahead of time just for the sake of time and making this video as short as possible. But I'll walk you through the steps that I did to solve this. So the first thing that I did is I drew a diagram for myself. That's always a good idea when we're working these style of problems, since we're connecting the area under our graph with the position of either a z-score or a data value. So here I have my normal distribution. I know the highest point right in the center is our mean, which is the 100.4. And the quartile 1 is referring to 25% or 0.25 of my data being underneath the curve starting on the left. So these normal distributions work kind of like a number line. The lowest value is always going to be on the left and then the highest value on the right. So you think of it kind of like a gauge being filled, that over here on the far left is 0, an area of 0 or 0% covered by my curve, and then that percentage is going to get greater as it fills up the area underneath until eventually if we covered all the area from the left to the right, it would be 100% or an area of 1 underneath the curve. So here, I know that I'm looking for on my chart what the z-score would be that yields this area of 0.25. So let's look at our chart here. And reading the chart really is, I'd say, kind of the trickiest part of this whole setup in this particular chapter, because you have to be very careful when reading your chart. I've done that several times where I make a mistake reading the chart, and then by the end of the problem I realize that I made an error. So it is something that's really tricky, and you have to really be careful when you read it. So here I'm looking on the interior of my chart for that value of 0.25. So we can kind of start reading it. I see the values are getting closer. And right in between these two data values that I see would be the 0.25. So how I figure out which one's closest is I could subtract my value from 0.25. So if I take 0.25 and I subtract this number I see here, 0.2483, I get a value of 0.0017. Here if I take this other number and do 0.25 minus 0.2514, I can see I get negative 0.0004. So the absolute difference, in other words, the smaller of those two numbers, regardless whether it's positive or negative, is the one I want to go with. So in this case, the 0.0014 is closer than what would have been here, which is 0.0017. So I'm looking at this value in my table. So how I would read that is I would look to the left, and the row is going to tell me my first digit, or the whole number in the tens place, I guess I would say. So negative 0.06, and then the header is going to tell me where the hundredths place or the second decimal place would be. Now here scrolling up in the chart, because it is a PDF, is a little tricky. So one of the things that I find helpful is counting from the end. So I know that this is the 9 value for the hundredths place, the 8 value, so this is 7. So I'm just counting backwards, 9, 8, 7. So then I know that the value that I have here would be a 7 for the hundredths place. So that's where my value of 0.67 comes from. Now, once I have that value, they're asking for the data value. So we have to convert that data value back from a z-score into the data value. And the formula you would use there is this one, that your data value x is your z-value times the standard deviation added by your mean. So I took my negative 0.67, multiplied it by the standard deviation given in the problem, which was 16.6, and I added the mean given in the problem, which was 100.4. And when I typed that into my calculator, I got 98.28. And then another thing to be mindful of here is how they want you to round your answer. So always look at the end of your box, there should be something in parentheses that tells you what to round to. So it says type an integer or decimal rounded to 1 decimal place. So if I round this to 1 decimal place, it should be 98.3. And we can see that that was the correct answer. Problem 9. So problem 9, 10, and so on are pretty similar. We're working between data values and z-scores and areas underneath our curve. So looking at this one, it says the survey found that women's heights were normally distributed with a mean of 63.5 and a standard deviation of 2.5. A branch of the military requires women's height to be between 58 and 80 inches. And part A is asking the percentage of women who meet the height requirement. So just like the last problem, we're going to start by drawing a graph. So here I have my normal curve. I know the number in the middle, my highest point, is going to be 63.5. And the two values that I'm looking at are 58, which is below the mean, and 80, which is above the mean. So really what I'm trying to find is this area in between that I shaded. So how am I going to do that? Well, step 1, anytime we're going from data values to area underneath our graph, our z-score is that step in between that we need. For me to use the area chart, I have to know the z-scores. So we're going to convert the 58 and the 80 into z-scores using our z-score formula. But the z-score is our data value minus the mean, all divided by standard deviation. So I calculated that for 58. I got negative 2.2 as my z-score. And then for 80, I got 6.6 as my z-score. And then the second step is to look those up in your chart to find the area underneath our normal distribution. So for negative 2.2, let's look at our graph here. So here there's 2 pages to this, right? The positive z-scores and the negative z-scores. So let me scroll up so you can see the side that I'm on. So here we're doing the negative z-scores. And I'm going to look for a negative 2.2. And what was the last digit here? Oh, there is no other digit. So it'd be a 0 in that case. So negative 2.2, and then the first column represents 0 for the hundredths place. So this would be my z-score, the 0.0139, which I can see here. Now for 6.6, that's a very large number. So that's actually going to fall off of our chart. So if I scroll up to the positive side, right, these are values that are positive z-scores, we can see that after 3.5, there isn't any values listed in the chart. And that's because our area is already so close to 1 that we almost consider it to be 1. So depending upon the problem, sometimes they do use 0.9999 for any data value for z-scores bigger than 3.5. Sometimes they round it to 1. And so it kind of depends upon the situation in terms of which one you would use. In this particular situation, because it is so large, the 0.9999, we would essentially just round to 1. Now here, if you look at our areas that we calculated, they're both coming from the left, right? So the value of 1 covers essentially all of my curve from the left all the way up into that 6.6 z-score, and then the value in pink is representing the value or area from the left up until the negative 2.2 z-score. So to find the area in between those two, we do need to subtract them. So we take the larger area and subtract the smaller area. So the area of 1 minus the area of 0.0139 yields an area of 0.9861. And then here, they want us to round to 2 decimal places, but notice that there's a percentage sign at the end of our text box. So the decimal that I got, I'm going to have to move my decimal place 2 places to make it a percent, right? So it'd be 98.61. So kind of be careful. I know that caught me up on this one. If you aren't careful in looking how they want you to type it in, it can become a wrong answer, even though you technically do have it correct. So just be mindful of how they want you to type it in. And then the next question is saying, would many women be denied the opportunity to join the military for being too short or too tall? So the 98.61% represents people that are allowed in. So the people that would be excluded is essentially the complement, or 1 minus that number. So let me calculate that really fast, 0.9861, which is a little over 1%, right, which is not much. So in this instance, we would say no, that it is not too short or too tall because it's only a very, very small percentage. It's just barely over 1% of people that would be denied. So that means we're, for the most part, including almost everybody. So answer choice D would be the correct one there. And for the second part, they want to know for the height requirement what the smallest height would be. Here they want the shortest 1% to be excluded. And then for the maximum height, if we want to exclude the tallest 2%. So again, I'm going to draw a picture so I can visualize what that looks like on my normal curve. So here we want the shortest 1% to be excluded. So we're going to be looking at what is the z-score and data value there that creates that cutoff. And then we want the tallest 2%. So I want the area on the right to be 2%. And again, determining the z-score and data value that makes that happen. So the first thing that we're going to do is find the z-scores that yield those particular areas. So here the area on the left being 1% matches what our chart looks like. So if I look in my chart for an area of 1%, sorry, I have to look from the left side here. So again, I'm looking on the interior of the chart, and then I'm going to read the z-score that creates that. So I can see this one right here looks like it's the closest, 0.0099. Here, this one's a little bit more, right? 0.0102 is 0.0002. This is 0.0001. So this is the closer data value. So I know it's 2.3, and then I need to determine the hundredths place. So you could just look at the top of the chart. Oops, don't want to lose it here, which is 0.03, or you could just count from the left. This is 0, 1, 2, and then 3. So our data value would be negative 2.33, okay, which we see here. Now the value on the right, we have to change that because our area in our chart is always from the left. So I'm going to take 1 and subtract the area on the right, which was the 2%, which means in my chart I'm going to look up the 0.98 value, which I saw as 2.05. So here we're going to look at the positive side. Oops. Okay. So I'm looking for 0.98. So it's really close in between these two numbers. It's closer to this data value than it is to this one, right? This is 0.0002 away versus this one's 0.0003. So this one is closer. So it'd be 2.0. And then looking at the column heading 5. So 2.05, which matches what we got here. So that's step 1 is get the z-scores, and then step 2 is to convert those z-scores back into data values, right? Because they're wanting to know the height in inches. They don't want to know the z-scores. So the formula when you want to go from a z-score back to a data value is this one here. Your data value is your z-score added, multiplied by the standard deviation and added by the mean. So I took each of those z-scores that we found and I did the calculation. So on the low side, it would be 57.7, and then for the high value cutoff, it'd be 68.6. And we can see that those do work in the question. Now, problem 10 is very similar to what we saw in the previous problem. Here we have a survey of women's heights that are normally distributed with the mean and a standard deviation. They also found men's height were normally distributed with the mean 69.3, standard deviation 3.2. And they said most of the live characters employed at the amusement park have height requirements with a minimum of 56 inches and a maximum of 63. And we want to find the percentage of men that fall between this height requirement. So similar to what we saw in the last example, there's like a lower value and a higher value, and we want to know the percentage in between those two. The only added element here is that we have two different data sets, that for men and that for women. But what we'll see when we go through this problem is we actually don't look at the women's data values. I'm really going to be focusing on the men's. All right, so I did break down our word problem to include, kind of segregate what is the woman's data versus the men's data and the requirements. So again, we're looking at the values in between. So if I were to generate that picture that we're used to seeing, we can see that the lower value is our 56, our higher value is 63, and we want to see what is that percentage in between. So the first thing that we're going to do is convert each of those data values into z-scores. So we're using the formula. The z-score is the data value minus the mean divided by standard deviation. So for 56, that's a z-score of negative 4.6. And for 63, that turns into a z-score of negative 1.97. So we can tell that this one's interesting because both data scores are negative. So my picture is actually not that accurate. It's going to be more like this, that we have the negative 1.46 here on the left, but then also the negative 1.97. So we're seeing that the percentage is actually both below the mean. So we can kind of see why this data would be a little biased against men, since the men's average isn't even being included. So to find the percentage on our graph, we're going to need to use the areas in our chart. So negative 4.16, that's a data value that exceeds what we're used to seeing. So if I go to the negative z-score side of my chart, oops, sorry, it's at the top here. We can see any data value that is smaller than negative 3.5, we would essentially consider our data value to be, or our area to be 0.0001. And similarly to what we saw in our last problem, sometimes we just round that down to 0, depending upon the situation. So in this case, because negative 4 is so extremely on the left, we're just going to consider that to be a value of 0, or an area of 0. Then I need to look up negative 1.97 in my chart. So I'm going to look at negative 1.9, and for the 100th value of 7, I'm going to then look at the column. So I'm going to look at the 0.07 column, look at where they intersect, and here is my value for my area. So it's 0.0244. And to find the difference between the two, now the left-hand side is 0, so subtracting by 0 won't change it. But if this was a value other than 0, we would need to subtract it. So the overall area is 0.0244. And then again, look at how our answer box is set up. They want the percent. So I would move my decimal place 2 places, so that's 2.44%. So we can see that that was correct. And then for the second part, it's a fill in the blank. So it says since most men, and we had the option to say does not meet or does meet. In this case, they don't meet the height requirement, right? We're saying that only a little bit more than 2% of all the men would meet the requirement, which is not much at all. So we can see that most of the characters are going to be women in that case, since the woman's mean is definitely lower than the men's mean height. Part B is asking if the height requirement were changed so that only the tallest 50% of men and shortest 5% of men were included. What would be the new requirements? So again, I'm going to draw myself a picture so I can visualize this. So the lowest 5% would be 5% of my area underneath the curve to the left, and then the tallest 50% would be 50% above on the right hand side. So here it's interesting because we would be essentially kind of taking off the whole right side of our graph, since we know the standard normal is symmetrical with 50% of the data on the left of the mean and 50% of the data on the right. So we're kind of disregarding the upper 50% of the data. So again, I have percentages, right? So the in-between step between a percentage and a data value is the z-score. So I'm going to need to look up the z-scores in my chart. So for the lower 5%, that's actually a special number. You could look for the area inside, but if you scroll all the way to the bottom of the chart, there's actually a little handy reference here. So 5% and 0.05% are meaningful data values in statistics, so that's why it's already here in the chart for us. So negative 6.45 would represent the z-score for 5%, which I have shown here. And then 50% on the right, we do have to scale it to represent area on the left. Well, in this case, 50% on the right, if we did 1 minus that 50%, would be 50% on the left. And you could look it up in your data chart, but that's actually just the mean of 0. So if you look at -0.00, there's our 50%. So that's a z-score of 0. So now we need to convert those z-scores into data values. So we're going to use the formula, our data value equals the z-score times the standard deviation added by the mean. So for -1.645, when we calculate it, that comes out to a value of 64 approximately. And when we do it for the 0 z-score, we get back the mean, which is 69.3. And we can see that those were the correct answers. The next problem, problem 11, here we have that they told us that our body temperatures are normally distributed with a mean of 98.2, standard deviation of 0.64, and the hospital uses 100.6 as the lowest temperature to be considered a fever, and it wants to know the percentage of normal and healthy people that would be considered to have a fever. So similar to all the things we've been doing up to this point, we draw ourselves a picture. So we know the mean is the highest point in the center, 98.2, and the fever amounts to the right of that mean, it's 100.6. And to be considered a fever, it's going to be values above that temperature. So we're looking at the area to the right underneath my curve. So again, I'm trying to get a percent value, but I have a data value. So the in-between step is to find the z-score. So step 1 is we need to convert our data value to a z-score using our z-score formula. So my data value, which is 100.6, minus my mean divided by the standard deviation, gets me a z-score of 3.75. So looking at my chart, I'm going to look at the positive side, or the page for the positive side of the chart, right here. And we can see that that's falling outside our highest number. So the highest z-score, -3.5, has 0.9999. So anything at 3.5 or above, we would either consider as 0.9999 or potentially 1, right, depending upon the scenario. And in this particular scenario, if I rounded it up to 1, then we would say that this right-hand area is 0. And that's not true, right? There's not 0 people that have fevers. There is some amount of people that do have fever. It's just a very small percentage. So in this instance, we're not going to round up this 0.999 to 1, because then it would lead to the false impression that no one has a fever. So this is the area to the left, right? That's what our data table is giving us. So we need to do subtraction. So 1 minus the 0.9999 is 0.0001. So we're just including the possibility that there's a very small percentage that does have a fever. We want the answer as a percent. So if I move my decimal place 2 places, that's 0.01%. And we can see that that is correct. Now the second question is, does this percentage suggest that a cutoff of 100.6 is appropriate? Well, yes it is, because the whole point is we want for someone to have a fever to be considered an exceptional case, right? In other words, a very small percentage of people would fall into this fever category. So 0.01% is a very small percentage, right? So we would consider that to be a good cutoff to determine whether someone is normal and healthy versus they have a fever. In Part B, the minimum temperature required for further medical testing. In Part B, they said they wanted the cutoff to be 5%. So if we changed our threshold for a temperature to be where only the exceptional high 5% of people were considered as requiring this testing, what data value would that be? So again, I'm going to draw myself a picture. That 5% is the upper 5%. So we want the area to be 5% on the right. So again, to go from percentage to a data value, the z-score is what we have to do as an in-between step. So I'm going to find the z-score that has an area of 0.95. Why I say 0.95 is because of how our chart is set up. We only get areas from the left in our curve, not from the right. So even though I'm looking at 5% on the right, we have to adjust it to consider that as area on the left. So 1 minus the 5% is 95%. So that's going to be what I look up on my chart. Now here, those are one of the exceptional data values. So if you look at the page that has the positive z-scores, at the bottom we can see they did list for us if you want to know a data value for 0.95 your z-score is 1.645. So here they pulled that out of the chart for us because it is a very special data value or area value in statistics. So the z-score is 1.645, and now we have to convert that 1.645 into the data value. So we're going to use our formula that the data value is your z-score times the standard deviation added by the mean. When we plug that in and calculate it in our calculator, it's going to round out to 99.25. And we can see that was the correct answer there. And problem 12 from the homework. We have the length of pregnancies have a mean of 270 days and a standard deviation of 15 days. And we want to find the probability that pregnancy lasts 109 days or longer. So this again is going to be very similar to problem 11 that we just saw. They're giving us a high value that's considered when something's exceptional, and we need to figure out the percentage, and then if they change that threshold for part B, what that new data value would be. So it's very, very similar to what we saw in the last problem. So let's first draw ourselves a picture. So we know the mean's 270. Our exceptionally long pregnancy is 309 days. So we're looking at the area to the right, values where the pregnancy is going to be a longer length than 309 days. So step one, we need to change that 309 into a z-score. When we put it into our z-score formula, we get that the z-score is 2.6. And then we need to look up that 2.6 on the chart. So on my chart, I'm going to be looking at the positive side. So here's our positive side. So I'm looking at 2.6. And what's my hundredths place? Oh, there is no hundredths place. So it'd be 0. So this first column is the 0 for the hundredths place. So this is my area, 0.9953. Which we can see here is the area on the left. So we do have to adjust since we want to know the percentage on the right-hand side. You would do 1 minus the area towards the left, and we get 0.0047. And we can see that was the correct answer. And then they want to know if the new threshold is to have a length of pregnancy that's in the lowest 4% to be considered premature, how many days that would represent for the pregnancy. So drawing ourselves a picture, we're now looking at values to the left. I want to have 4% on the left as the area underneath my curve. So I'm going to look up that 4% in my chart and determine what the z-score is. So I'm looking at data values on the left, so I want to have the left side of my z-chart. And so I'm looking inside my z-chart for a value of 0.04. Okay, so we can see this right here is the closest value, 0.0401. Either one on either side is going to be a larger distance away. This is 0.009. This is 0.0008, so this is the closest one. So I would read the row negative 1.7, and then the column is 5. So that's where we got our negative 1.75 from. Then we need to convert that z-score into our actual data value. So I plug in my z-score, I multiply it by the standard deviation, and add the mean, and that comes out to approximately 244 days. And we can see that was correct.